Okay. Yes.
So I want to spend just two
Yeah.
words on that. The objective here was try uh, to design a tool to help the engineer, the scientist in general to apply the ideas of embedding physics. The objective was quite ambitious, and I mean, because was to try to help the scientists not only in the part of the design, but the initial objective was to try to help in all the phases of deployment of this kind of network. Commonly because the objective is not only to design, but also train and deploy maybe in a real hardware. Okay, so the objective was to try to help the scientists to apply directly in the hardware what they are designed. And the focus was try to give some blocks, some libraries of physics embedding, okay, in the networks, supporting different approaches. Most of the one we saw, okay.
Yes. Yeah, indeed. Here we call physics embedded neural networks, but just to summarize all the approaches, so physics guided, encoded, and informed learning approaches. Yeah.
Okay, so we called NNODELY for the jokes. I mean, these are double N and N, and that is become an M. Okay, so as we said, as we said before, the framework try to give you the building blocks to implement physics guided, physics encoded, and physics informed neural networks, implementing the feature you need to implement those approaches. The objective, mainly the objective of the framework was to the dynamics learning. Okay, most of the example we will see in the next slide are focused on dynamics learning, control, estimation also. The framework will help also to try to create complex network that combine different blocks. The idea was creating something that is similar to, I don't know if you are familiar with MATLAB Simulink. Okay, try to give you a way to combine networks in a chain, creating a more complex architecture, and then maybe extract or export piece of these networks for your real application. So this was the idea. So helping to design to dynamics learning, control, and estimation of physical system in general. Of course, due to the fact that commonly writing neural networks in a standard PyTorch, TensorFlow, maybe can be hard for someone that comes from a specific domain, for example, chemistry or engineering. Sometimes can be harder to design these networks. And the idea was to try to help the scientist to prototype this network for physics guided, physics encoded, physics informed neural networks. Yeah, support the scientist. The other things that I want to say that when we started to design was not so popular is the fact that now maybe using LLM, someone that comes from different field can already try to use machine learning in their research, but still using black box approach, like asking to LLM to do something in, I don't know, PyTorch or TensorFlow, maybe is not sometimes the best way to approach a problem. So for this reason, I still think that try to use a software that help you to design this network, help you to create a very complex architecture instead of writing standard torch can still something that can be useful. Also, the objective of the framework try to collect different approaches that come from literature, give a simple way to use it. So I thought a specific, I have an idea of using NNODely in combination with physics inform, in combination with model structured. And in this way, the idea was to help you to make this simple, okay? Instead, because each software have their own library. For example, NNODely have their own library. Beans have their own library. What we try to do is try to merge this approach and helping the scientist to use those. Okay, so, and finally, what I said before, a repository of incremental know-how and examples. So try to collect what we learn inside a single repository, and and hope that this will be used from the community, and maybe some point the community try to put their knowledge inside this framework. This was the main idea. Of course, the framework is open source and is released on GitHub. So you have the repository if you want to have a look. Is open source, and here we reported all the phases that I when I wrote the main project that is, I mean, from where I start to think about this software. I try to design the pipeline, the general pipeline that want to cover with the model. So the idea was to give an help in the definition of the neural model, and help to design and to structure the dataset. So starting from raw files, commonly CSV, now we are expanding to different files, help you to build your dataset based on the information that comes from the neural model. So you design your neural model, you get the neural model is used to build the dataset. Then using the dataset and the neural model, you train the model. Also during the training, the idea was to incorporate some tricks, some ideas that maybe some specific layer needs to working better. For example, some if you remember yesterday or also this morning, we applied the computational module, the linear layer, that the definite impulse response. For example, the initialization of definite impulse response can be done in some specific way. So, for example, including the idea of the dynamics, the typical dynamics of single pole to help the learning or other ideas. So also the training phase is tried to be in some way supported, okay, using some specific advantage that you not find directly in a standard PyTorch framework or a deep learning framework. Then you get the model that you train, and using some other part of the dataset, you can validate. I reported also validation because, as I mentioned at the beginning of the course, also validation can be in some case model based. Okay, so you can have specific algorithm to validate your model in your field. So the idea was give the possibility to easily to try to validate also in your specific in your way your model. we already include some additional evaluation of the model that are not only the RMC, but are, for example, the Eichhorn criterion that is used to validate different model and validate which is the best considering the number of parameters. But the idea was to improve also this part. Then you get a validated model, and the idea then will be to easily combine this validated model to another additional neural model that you design. For just to be clear, you create your system dynamics, then you validate your system dynamics, then you combine your system dynamics with a neural controller, and then you get a huge, bigger network, okay, combining them together, okay, so the framework help you also to combine different subnetworks together, and then you train again, and then you can process this loop until you reach a complete model. Or the other possibility, for example, is to build and design a specific part of your model, and then you combine with a more bigger part of your model, and then you have a combination of submodules that works together. And then finally, you can export your network. Also in this phase, the idea was to help you to extract maybe piece of the network, the whole network in an easy way and export. Now we are exporting, we have the possibility to export in native PyTorch if you want to include in your code, or in NNX, that is one of the standard tool for exporting neural networks. Okay, easy to install. Now we are at the version 1.5.5, and now we are going to give a big release. We are working on that to including additional features that will help to use NeuroLOD or other approaches that we see. So now it is working. All the tests, we have a good coverage on the code we brought, around 90%, 95. I don't remember how much was. And of course, for the new release, we will see next year. Okay, so we have our first example. This was a very, very old example. The paper, probably some of you know pretty well this work, and this was of the first one on this topic. That, I mean, with Mauro D'Alio, that was the professor that I was working with. We started to design this neural network architecture with a specific structure, and was the 2019 at the moment. So our knowledge comes from I mean some years ago. Okay, you want to say something about this part?
Yeah, indeed. So this is just indeed. So these are some examples, yeah, in the field of autonomous racing. Yeah, as Gastone said, yeah, one of them is.
Yeah, he's not.
Yeah.
He's not.
Yeah, the other ones are a bit more recent, but yeah, it's a collection of examples, yeah, from autonomous vehicles and autonomous racing. Yeah, so of course, yeah, the first examples will be in autonomous racing because it's a challenging field, yeah, that we work on. Also, we worked on with Gastone. I work on in TUM. Also, other people here work on that. So you know the challenges. Actually, we have. To be, of course, we need to build a test bed for autonomous vehicles, right? So this is the motivation. Push the vehicles where you can be safe on a racetrack, but then try to gain some insights and transfer them to public road cars. So yes, on circuits we can simulate the operation in emergency scenarios, and we can essentially still be safe, yeah, without creating damage, especially with the autonomous vehicles. Still, there are some challenges, yeah, like the nonlinear dynamics. The faster you go, the more nonlinear your dynamics gets. So a simple, fully connected layer is not enough. You have to learn the dynamics. We need something more. We need also to make decision-making in adversarial scenarios. Like in this case, we have to overtake actually our opponent. And this is what happened in the last Yas Marina race in Abu Dhabi. It was several months ago, but this was an overtake of the Toom car against the one from the University of Modena and Reggio Emilia. So this is an example, yeah. So there we really need to be complex with our methods, right? We need to model the nonlinear dynamics. So physics-based models also struggle many times. We need something more there. And for this reason, okay, one can use a hierarchical motion planning and control scheme, right? So we have some modules that do motion planning, some other modules that do motion control, like in this case, feed forward and feedback control. And then we need to control our vehicle, right? And we will have some estimators for the vehicle pose and state. But this is, of course, one possibility, very popular in the literature. Because it's modular, it's basically more interpretable than fully end-to-end, of course. So let's start to see how we can actually learn the vehicle dynamics. So basically, here we will be exploring model structure neural networks to learn first the longitudinal here, vehicle dynamics, and this is what Gastone was talking about, and then the lateral and combined vehicle dynamics. So of course, these are examples in this field because we come originally from that field, but later we will see also examples in different fields, and actually the framework and the ideas we presented are very broad, and they can be applied, of course, to a broad class of systems. So here we want to learn the longitudinal vehicle dynamics, so in the longitudinal direction mainly. So our inputs can be the pedal, as we said yesterday. So the pedal P, if you think of a throttle brake pedal, you condense it into one variable. Then pedal greater than 0 means acceleration, means throttle. Pedal negative means braking. Another input can be the speed, okay, the current speed of the car. And based on that, we want to estimate the longitudinal acceleration. Okay, so we have only the pedal and the speed, and based on that, please tell me what is the current acceleration of the car. So of course, one solution can be multilayer perceptron, yeah? So we take our data, measured data, pedal, speed, acceleration, we feed them to a black box neural network, we get it. But actually, I mean, we can do that, but typically it's a bit data hungry, so we really need to have a lot of data. We actually know the vehicle dynamics in this case, so it would be a pity to use such a black box model. We can do maybe something more by embedding some prior insights. So let's start from what we know. Yeah, what we know is the Newton equation on the longitudinal direction. So basically, we know very simply AX, so longitudinal acceleration, is the sum of the forces divided by the mass. Yeah, very simple. But let's expand the term. So here we have longitudinal sum of the forces means, in this case, the force at the front axle, FXF. This is a function of the pedal. The function of the rear axle, FXR, again, a function of the pedal, minus the aerodynamic drag. In this case, we have, which is a function of the V squared. And the thing is, yes, this relation is correct. But in practice, expressing the relation between the force, Fx, and the pedal is a bit complex, yeah, because basically here we have a lot of dynamics in between. When we push the pedal, we have the pedal dynamics, we have the actuator dynamics if we have an electric motor that has some delay, has some inertia, has maybe some backlash. If we have a combustion engine, even worse. We have maybe turbo lag, we have a lot of effects to consider. Plus, we have the tire dynamics, okay, because then the engine transfers the torque through a gearbox maybe to the tires, and the tires are super nonlinear. They are super nonlinear. I mean, at a certain point they saturate. They cannot give you extra force if you push harder. Maybe there is a decrease after the saturation. So it's very complex to model these things. Here we say, okay, let's try to rewrite this relation in a neural form. And what we can do is indeed do not try to keep the relations we have here. Okay, so here we have three forces, basically. So in our neural network, we also want to have three forces that then are summed together. So the first branch will be the aerodynamic force, FD. And we know, again, it depends on the squared of the velocity. So let's try to keep the relation. Here we can use maybe a more general relation rather than a single coefficient. That's fine if the aerodynamic model is actually more complex, like in the case of high aerodynamic race cars. And then the other two blocks. So for example, this block here, the last layer is estimating FXF. So the first one, in this case, the vehicle can be rear-wheel drive or front-wheel drive, okay, doesn't matter, but the last layer is basically estimating a relation between the pedal, P, and the front and the force and the front axle, okay, through a neural network or through something more specific that we can design. And the same thing for the second block. The second block is estimating the force at the rear axle. And as we said yesterday, we know that, so if at the rear axle we have only braking forces, because the vehicle is front wheel driven, then at the rear axle, we don't want to have positive forces. We only want to have negative forces if we're braking. And so basically we can extract only the negative part of the pedal through this negative ReLU function that is basically extracting only the negative part of the pedal. The positive part is clipped to 0 so that it won't affect this force. And in this way, we're sure that this branch is actually learning only the effect of a braking force at the rear axle. Okay, and it's not messing up with the positive traction force. So this is a simple relation. And note we have a plus sign. So again, superposition of effects. We don't want to forget that. Here we find a single value for the pedal. You find a single value for the pedal at the current time step. But as we learned yesterday, actually having a past window can help in better modeling the dynamics in this case. So we can plug in here actually a past window of pedal values up to a certain time step n. Yeah, okay, later we will learn how to design maybe this n. So actually how long we actually need to look into the past to be more accurate than the current time step. And in this case, if we use past windows here, then these branches, these two fully connected layers, if they are fully connected layers, then they take the meaning of a neural finite impulse response, yeah, as we've seen also in the recap this morning. So basically, these layers are just learning the indeed the finite impulse response, so the discrete time transfer function of the system. Exactly.
To the
from the past window of pedal to the acceleration.
By the time.
Yes, or to the force, yeah, and later to the acceleration. Yes.
Of course, this is reported as a force, but is a sum of accelerated force divided by m. Yeah, is
yes, indeed. Yeah, that would be at the end a normalization by m that here we don't report, but basically it will be learned by the layers themselves.
Split the coefficient in the list. You can also add another coefficient at the end that try to merge, but they are linearly related, so it's impossible to distinguish between m and.
And of course, this is still a simplified relation, right? The one at the top. Now we will introduce other terms, but this relation is still simplified. So we don't want to simply rewrite this relation in a discrete time form because we know it would be still simplified, yeah? So here the idea is, okay, let's not forget the basic ideas, the basic principles, but let's also generalize them a bit, right? So we have here basically neural modules that can learn more than what Newton alone would be able to learn. And okay, in general, we can also have the gears, as we said yesterday. So in general, this relation between the pedal and the force, the generated force, can be complicated if we have different gears, G, because this is a discrete variable, right? And so what we can do, instead of having only one fully connected layer here, is we can have a neural compositional module, as we said before. We can call it psi1, and it's basically, if we expand it, it's basically containing maybe several fully connected layers along parallel branches, and each of them will be activated by an activation function, phi, as we discussed previously.
This is a rectangular activation function.
Exactly, yeah. In this case, yeah, G is a discrete variable, is a discrete time, not only discrete time, but also discrete, a quantized variable. So it doesn't make sense maybe to use continuous activation functions phi, but rectangular ones should be more effective in this case.
Also in this case, as we mentioned at the beginning, yesterday, that you can,
Yes. So we said at the beginning that, okay, in the framework we presented, these fully connected layers were actually appearing after the activation function. But we said in some cases we can still swap them. In this case, we actually swapped them because G is indeed a quantized variable, a discrete variable. So it's not so helpful to take into account also the past history of G. I mean, we can, in principle, we can, but maybe it's not so useful. And so we decided to basically compress the time dimension that we have here in the inputs. Here we have a time dimension of n+1 vector elements. We compress the time dimension here. So here the output will be a scalar. And then the scalar is multiplied. So this is not an element-wise, this is a simple multiplication between the scalar and its activation function. And then we take a sum at the end of all the blocks, of all the channels, yeah? So yes, if we have the gears, we can do that, for example. In general, this was the pure longitudinal dynamics, but in practice, the pure longitudinal is always affected by the lateral dynamics. So if we also add some steering, then our acceleration typically decreases. Okay, so if we are pushing the pedal, but also steering, then typically we can accelerate a bit less than the case in which the steering angle is 0. And indeed, Newton knows this, yeah? Newton equation tell us that in general, we need to subtract a contribution due to the lateral forces Fy, so in the lateral direction, times the sine of the steering angle. Okay, this comes from a vehicle model, single track vehicle model. It's a simplified relation, but still we can plug it in our neuralized setting. So we can say, well, I want to have a branch that estimates Fy somehow, and another branch that gives me the sine of the steering angle. And then I take the product and I sum to the other forces, like described here. Or basically I should subtract, but who cares? The neural network will learn it, yeah? And basically, yeah, here we're doing something similar. So we also don't know the relation between the lateral forces and the vehicle quantities, yeah? So basically, we cannot measure the lateral forces directly. What we can measure is the velocity, Vx, the lateral accelerations, Ay, from the IMU sensors. So maybe let's use another neural compositional module, psi2 in this case, to combine the input, so Ay, a past window of input, with the velocity. So basically, in this case, the velocity becomes a scheduling variable, can become a scheduling variable. And the real input is Ay. So the model will learn to use Ay with a certain logic to estimate the lateral force and maybe change this relation as a function of the speed. And simply, yeah, so here again, you can have also another small neural network that preprocesses the steering angle, because maybe we cannot, this would be the steering angle at the ground, yeah, so the physical steering angle of our tires, but we don't know that, yeah, it's a mess to measure that. So what we can measure is the one at the steering wheel easily with an encoder. And what we can do is then to preprocess that steering angle at the steering wheel with a neural network that can implicitly estimate the one at the wheels, at the ground. Okay, it will estimate, it will help us do that. And then, yeah, we can preserve the sign operation if you want, and take the product with FY. Okay, so this is a simple model, quite simple model, but still one of the first examples we can build with this type of. So this is a model structure neural network, yeah. And by the way, okay, we said these are Psi1, Psi2, but what about the other layers? Yeah, so if you look carefully, you can still interpret, for example, this layer as a neural compositional module Psi, because it's true that we don't have the full structure that we presented before and yesterday. So yes, we don't have the local models here. We don't have local activation functions. We just have basically
the non-linearities plus the...
Exactly. We still have an input non-linearity, which is the square operation. And we have an output function that can be this one. And so it can still be interpreted as a neural compositional module. And same thing for the others. Yeah. So same thing also for this one. Again, input non-linearity and fully connected layer. So we can interpret everything at the end as neural compositional modules. And you see, in this case, we're taking sums and multiplications of neural compositional modules to obtain our final output at the end.
Here, the take-home message is that there is no a free lunch to apply this approach. No, so I mean, you need to know your system, to know the physics behind what you want to model, and then you can try to put some effort in doing this work, and this work maybe will help to reach a higher level of fitting of your system, no? Because we go a little bit beyond the standard Newton, because we add more flexibility to the system to learn what was not represented from the equation. Okay. But of course, it's not free. No, you need to know what is your system, and you need to put some effort to try to design your best architecture. We try to give a block that works in most of the case. Okay, but of course, then you need a little bit of.
Yes, indeed. Yeah, so indeed, a good point. So we have, in general, well, we will see in the examples later today, in the other examples. But we have different ways to come up at the end, or to design a model structured neural network. So in this case, we took the approach of starting from the Newton equations and then rewriting them in the form of neural compositional modules, which give more flexibility to the Newton formulation. But this is not the only possibility. In some cases, maybe we don't have a good Newton model to start from. In that case, we can directly start from the full formulation of a neural compositional module, and we try to apply it to our system. So in other cases, we also do that. So we start just from the full expression of a neural compositional module, and we try to see how we can adapt it to our system by injecting some prior knowledge if we have it. Right. Yeah, questions up to here? Curiosities, yes.
It's online. Sometimes we.
Yeah, so indeed, this is the formulation. Do you have a question? No. Okay. Also, okay, this was the formulation, and then this was applied actually to the data with a real car, where we applied it to different cars. And this was an example with the.
Yeah, this was the paper I mentioned before.
Yes, it is from 2019. Yeah, it was one of the first applications. And we can see here the distribution of the signal. This is the longitudinal acceleration at the end. So we have the comparison with the acceleration. Yeah, the measured one. Yes.
Yeah, the top, the green, the light green was the unstructured
the
network,
general purpose.
General purpose black box neural network that just take all the inputs, create a one single vector, and then combine with some layers. And that's
Yes. And the second one is actually the model structure, the version that we presented before. And then we have the measured acceleration. Maybe here you cannot distinguish them very well, but you see, for example, in this region, at the beginning, you see the difference. Also here, so sometimes the unstructured or the general purpose network underestimates or overestimates, while our version is more accurate on unseen data. And these were actually unseen data in the validation set. And yeah, so this is the main intuition. You see also the gears. The gears change the ones, I don't see the coin in blue, okay.
Yeah, the blue.
You see they change discretely, yeah. So maybe here we kept the fourth gear, then changed to third gear, second gear, first gear, and so on. So this is something that changes the dynamics. Yeah, we need to take into account this, otherwise we will have a wrong prediction at the end, yeah. And this is another insight, yeah, that is maybe useful to have. Maybe many people in the machine learning community don't look at this, I know, but it's the power spectral densities of your residuals. So it's related to the Fourier transform, if you want. It's a power spectra, so it gives you an idea of what is the frequency content of your residuals. Yeah. So you see here the residuals of so the difference between the predicted and measured acceleration. These are the residuals for the unstructured model. You see they have some power here, and the power of these residuals is always higher than the power of the structured, of the other structured network, especially in this range of frequencies. This is frequency in hertz. You see it goes up to 10 hertz, and there is a reason why. And then you see the signal. The signal is in black, the real signal, the measured longitudinal acceleration. And then you also see the noise in pink. So here I think we estimated the noise from the parts in which we knew we had only noise. So basically probably driving at constant speed, where we had no acceleration, and there it's only noise. Okay, so we collect some data points there. We take the power spectrum with that. Of course, it's more noisy because we have fewer samples. So the more samples you have, the cleaner or the smoother the power spectrum you get. But still you get an intuition. So you see after yeah, okay, first of all, our residuals have lower power. So this means better dynamics learning. This means the residuals have lower magnitude, if you want.
Yeah, we are close to the noise.
Closer to the noise.
But not below.
Yes.
Otherwise, yeah.
Exactly. If you go below the noise, it's a problem because then you're overfitting, basically. If you go, so if this line went below, if the green line went below the pink, then it means we are overfitting, basically. So it's another intuition you can have from this diagram. Yeah, it would always be good to plot it after you train your model.
Yeah, of course, here you can apply this model because if you apply in a network that have hundreds of neurons, this analysis may be not really useful because probably it's too wide the space that you are looking for. But for this model that are really similar to a standard approach using a standard method that come from analysis of signal, analysis of linear models, it works.
Yeah. Well, but in any case, it doesn't depend on the model complexity. Yeah, this is something that you applied on the signal.
Yeah, you can. Yes. This is true. Yeah. You can of course apply to a more complex model, but yeah, when it is very, very non-linear, then what you get maybe is not.
Yeah. So this is something you apply to the signal itself. So after you compute the predictions with the network or with your model, you can simply take the power spectral density. There are tools to do this in Python, MATLAB, whatever. And this diagram still gives good intuition because you also see that the signal to noise ratio drops significantly after 2-3 hertz. So here it's in log scale, but this will be 2-3 hertz. So here you see the signal has the same power as the noise.
Yeah.
Then it means we lose our frequency content. So basically, after 2-3 hertz, it's only noise, practically. And this is a mechanical system, so it makes sense. I mean, for a vehicle, but also for other types of mechanical systems, the frequency content, the good one, the one we really want to learn, is maybe in less than 5 hertz, right? After 7 hertz, we start having vibrations, only vibrations, for example, engine vibrations in this case, or other vibrations which we don't want to capture because we don't want to model vibrations here. We want to model the overall vehicle dynamics or system dynamics. And so this gives us an intuition. We don't want to model something higher than 3 hertz in this case. And so we can also try to exploit this intuition somehow. So yeah, in the neural network design, at least in our model structured neural network design, because we said we have some input windows, yeah. So here we have some input windows that go to our model, and here we have a certain discretization. First of all, okay, so we have a certain time step to discretize these input windows, and then we have also a length of the input windows. Okay, so we know our frequency content is basically included in 1-3 hertz, which means that typically, okay, 1 hertz means 1 second, 3 hertz means 0.3 seconds. So this means a past history of basically 1.5 seconds is enough for what we need, yeah. We can also use, I mean, if we use the shorter windows, then we could not probably learn the low frequency content so well. If you use shorter windows. If you use longer windows, you can do it, but maybe it's not so useful because your dynamics is concentrated in this time and frequency range.
And then we will see what will be the result of those layers here in the finite impulse response, looking also to the weights, we can understand.
Exactly. So by looking at these weights at the end, we will see an example later in which by looking at the weights of the fully connected layers, of the trained weights, you can get an intuition of the time scale also of the system. But in this case, we got the intuition from the power spectra. Fine, yeah, that we can still do that. And by the way, okay, so here we say, let's take N. So N is the discretization or the number of points for the pedal P. M is the number of points for the acceleration, the lateral acceleration, and the velocity here. So let's take N equal M equal 25, for example, with a discretization time step of 0.05 seconds. And then in total, if you do N times 0.05, you get 1.25 seconds, which is an acceptable time scale. I mean, it's what we need based on our analysis. And by the way, this time step also plays a role, yeah, because this one means 20 hertz. And if you have a discretization at 20 hertz, that's your frequency. And then you know that, I mean, this is related to the bandwidth that you can capture, right, with the Nyquist theorem. So, so basically this tells you that, first of all, in the power spectrum, you cannot look beyond 10 hertz because your discretization frequency is 20 hertz. And this also means that your bandwidth that you can really capture is limited to 10 hertz. But it makes sense. I mean, for a physical system, again, it's what we need. And again, we can also use we can also use different values for N and M. So for the longitudinal input, which is the pedal, and the lateral input, the acceleration, lateral acceleration, because maybe we know that the longitudinal and lateral dynamics have different time scales. So we can do that. In this case, we keep them the same, but in principle, we can change them. And yes, we can use also higher values, but then we probably risk overfitting because we are learning something that is non-physical. So you can use longer sequences, but intuitively, if you do so, it means the network learns also patterns in your data. Because if you use 1 minute of past windows, it means the network learns what is the correlation between this 1 minute of history and your output. So you risk also learning correlations that you don't want to learn. So long time correlations that you don't want to learn.
That are not physical.
That are not physical, yeah, because maybe after 1-2 seconds, your output becomes uncorrelated with the past input, or the correlation is very low. Okay. Questions here? Yeah.
Spectral density was computed on the training.
I think this was the validation set, but I don't remember.
Yeah,
In principle, you should put it on the whole amount of data.
Probably was of the whole.
Because the more data you have, the cleaner the power, the spectrum.
Probably in that case was all the data.
The whole, yeah.
Yeah. If I remember.
Interesting to see the training.
Yes, yeah.
Between the two.
Yes, exactly. So in principle, one can compute 2 power spectral densities, one for training, one for validation, and see the difference. Yeah, because maybe in training you see that you are overfitting, then in validation you're not, or vice versa.
Commonly, from my experience, using these networks is very hard to overfit.
Yeah.
Commonly hard because the number of parameters is not big, and the architecture, I mean, helps you to avoid this problem. Commonly. Yeah.
Yes, exactly. So in general, no, yeah, I encourage you to take a look at power spectra as well after you train your model on a physical quantity, especially. Yeah. Okay. Yes. So indeed, we discussed these intuitions. If you want, we can maybe take a short break, or we look at the code directly. Maybe okay. Let's look at the code and we take a break. So indeed, yeah, we have the code for this model. In the PDF, you also find the link that brings you directly to the code, to the NNODELY applications repository, which is another GitHub repository. But
many of the application
yes, but we can take a look directly. We have it here open in VS Code.
Here, the only difference between this is the model that you have in the paper. Okay.
Yes.
There is a small difference between the one is presented in this slide because we have is not included the lateral dynamics in the model that you will see in the code.
Yeah, so
but
basically
include an additional branch that try to compensate and measure and estimate the force due to the slope of the.
Yes. So this part of the network is something that we presented here during the lecture, but is not included in the original paper. Yes.
Paper. And the code was reported the original results.
Yes, and the code is for the original paper. And plus here we have an additional input, which is the altitude.
The altitude of the
road. Yes, if the car is driving on a 3D road, the altitude plays a role because it can accelerate more the car, basically, yes. And so here you see the code. It's called the Model Longitudinal Vehicle Dynamics. So by the way, this is our repository with all the applications we collect. Yeah, sorry. Zoom in. Yes. This is better? Yeah, no, I just wanted to show. Okay, here we have all the. I can also zoom more. Yeah, here we have all the applications. Yeah, in the repository, which is all open source. So we have some applications that are in vehicle dynamics, but later or tomorrow we will also see some applications with other systems. Yeah, mass spring, also physics informed, the neural networks, pendulum, friction estimation, equation learner, and others. So the target of this repository is also to collect the know-how. Yeah, so we want to collect all the examples we have, not only with model structured, also other types of physics embedded machine learning in one repository. So it's useful also for the community to have a look and to build on top of that, to use it as benchmarks or whatever. And so in the vehicle folder, we actually have quite a lot of applications. One of them is with the what we call model longitudinal vehicle dynamics, and it's the one you see here, right? So I hope it's big enough. Yeah, we can also minimize it here. So first of all, I would say the number of lines of code. Yeah, so this is 59 lines of code. Still, there is something that can be avoided, like this filter function, like something that is really for.
This was
yeah.
to replicate exactly what we
Yes.
did in the paper.
Yes, but the target is really to have at the end a compact code. Of course, it's not always like that. In this case, the model is quite simple, but at least if you do things carefully, you can really write things in a compact way. And because basically the core of the library helps you a lot in doing that. And so, yes, in this case, we have
We were two different. N is representing the variable that needs
yes,
a
it's
pass
this one, basically.
window in time. Is that and A was the vector for the, as I said before, the altitude
yeah.
representation, because the altitude representation was a vector, so the input is a specific long vector of
Yeah, so here we had another input that was representing the past altitude value.
the altitude
Yes.
value. Yeah.
And then yes, here we have the definitions for all the inputs. So we need the velocity as an input. We need the brake. Okay, in this case we had the brake and torque. Yeah. So in this case we have one single input. In the paper we actually had the brake input and the and engine torque as separate inputs, but conceptually there's no difference. Yeah. We have the gear as an additional input. We have the altitude, as we said. And then we have the acceleration. Yeah, here you find it as an input, but actually it's a signal for the model. So maybe instead of inputs, we should call them signals, or I don't know.
Yeah,
but
the idea is to all the things that go inside the network for make training or inference are called the input as general
yes.
Input of the whole architecture, because we consider architecture of the network the part related to the loss function plus the architecture itself. And so for this reason, what we call what is taken from the data set with the same name, that is input.
Yes.
Okay, is design choice.
Yes, and then yes, here you find basically the network topology is here in these 6 lines. Yeah, so you want, for example, one branch is for the aerodynamic drag force. Yeah, so you want it to be proportional to the square of the velocity.
This is how Python.
Yeah, and we want just to have the current velocity, right? We don't want to have a past window here. So by doing velocity dot last, we extract only the last value of the velocity.
Yeah, the framework, because we're working a lot of time window in general. So in the code, it's very easy to extract a single sample in time or a past time window. In this case, we get a single past input. Okay,
Yes.
so one single step. And for example, if you go
also in the case of the gear,
we get the last.
So we only want to have only the current gear GK. So we do gear dot last.
Instead, for example, for braking, if you go at the end there, brake dot sv, that is a shortcut for sample window. We get n sample steps.
Yes, so
this is build. This operation will build automatically the sequence, and also you don't need to take care about creating a sliding window in time from your dataset. This is something that the framework will think about this slicing, and then.
So also for brake, you need a sample window, and also for probably the corresponding engine torque, which is here. For the engine torque, you need as well a sample window, so SW with the same length N.
Yeah.
And then here, yeah, we define the single layer. So for the aero drag, we just want to have
one single.
Yeah. So this is not a real fully connected layer, but rather, if you want, a coefficient, a learnable coefficient.
That is representing
yeah.
really the aerodynamic drag, the simple aerodynamic drag.
And so in this case, we can have, yes, a linear layer. So linear defines a linear fully connected layer, if you want.
And the dimension of the linear depends, of course, to the dimension of the input. In this case, these are single elements, and so these are just a scalar.
Yeah, you can also give the output dimension, you see, for the linear, in the case you want to have multiple outputs. If the fully connected layer has more than one neuron, you can have an output dimension that is larger than 1. Probably if you don't say anything, it means output dimension equal 1. Yeah. So this is our case. So by default, we have 1 neuron there. We can have be equal true says that we want to have a bias, probably, right? So we can learn, we have actually 1 weight and 1 bias in the layer.
This is because it's try to estimate the rolling friction.
Yes, exactly. Yeah. So yes, we can have indeed aerodynamic drag plus rolling or static friction there, modeled by the bias. And then we have to simply implement this branch here. So we want to have a negative value and then a fully connected layer, which we interpret, as we said, as a finite impulse response layer, so FIR layer. And even in the framework, we call it FIR layer. So this is indeed modeling a finite impulse response relation in the neural network model. And so basically we want to say that we want to have a minus value, okay, so a negative value that takes as input the FIR layer. And the FIR layer has then some arguments, right?
Yeah, is a way to initialize the weights.
Yes.
Particularly here, we initialize the weights using a negative exponential. So we get already a shape that is probably the one.
This is something we will see in the next application. We will look at the trained weights. But if you look at the trained weights for this, for this branch here, you will see they have a certain behavior. In this case, we have the past inputs in the past, and then we have the present input. So intuitively, the network will learn that the present has more impact than the past, right? So the present is typically more impactful unless you have time delays in your big time delays in your
system. If you have a big deal, what we will see that you can also interpret the weights to understand what is the delays of your system, because where is the peak of the intensity of the weights in your finite impulse response, you can this highlights the position of your delay.
Yes,
the amount of the delay.
But in principle, we can say, okay, we expect to have an exponential shape for this way, for the trained weights, because we expect the present to have more impact than the past. And so we can say this to the model. We can say, I'm expecting an exponential shape for the inputs, for the weights, sorry, and this will be used as initial guess. So rather than starting from a typical initialization, which is the Glorot or Xavier or a random initialization, we can say, no, please start from an exponential shape. And we can also say, okay, what is the first value? So the highest value for the weight. Okay, this is something maybe more tricky to say in principle, but at least we expect to have an exponential. Okay, this is important. And we take as input, the past sample window with n time steps for the brake pedal. Same for the, okay, then we have the gravity force. Here we don't have it. Yes, we don't have it.
Here there is an intuition related to how we structure the code, because the input of the network for the altitude and for for example, for the gas pedal are both vectors, okay? Because you have the vector that is representing the altitude, the other one is representing the time, the gas pedal, but one is in in time domain because you are taking information related to the time. The other one is because in this paper the gravity was computed by computed the altitude around the vehicle. Okay.
Yes.
Is around the
So
vehicle.
in the data set in this case, so the signals in the data set, so like the velocity, the
And
brake, the gear, the torque, the acceleration, they are in the time domain, right?
Time domain.
So they are sampled with a certain discretization in a data set. But the altitude signal, we don't have it in the time domain. We have it only in the space domain, right? So along the road. And so we can still use it. Yeah, we can still use it in the data
And this
set
is
as
the
is.
motivation why you have a specific dimension, because
Dimensions, yeah.
these are a dimension in space. And for this reason, we use a linear operation and not a finite impulse response, because they are working into different subspace. Yeah.
Yes, okay, it's maybe it's
It's
not
a
so
little bit,
intuitive,
yeah.
but yeah, okay, there is a reason why we write here linear and not FIR, even if in principle they are both linear, fully connected layers. But one, the FIR compresses the time dimension, as we've said, yeah, while the linear probably compresses the space dimension, yeah. But in principle, you can use them.
This design choice there is because commonly when you are working on general purpose deep learning framework, you are a vector, and doesn't matter if this vector is representing time or space. But because we are scientists, we have a clear understanding if we are working in time or in space. And for this reason, I want to highlight also to helping you to decide what is the dimension that you want to squeeze.
Yes,
yeah,
of course, this is something a bit technical. Maybe you don't get the difference, but okay, we can still say you can do that. Yeah, so you can have a data set with the different dimensions inside, a time dimension, but also space dimension, or you can interpret as a different dimension. Yeah.
And then there is the
yes, the other branch,
function
the
pacify,
yes,
that is used to design to build the rectangular function.
Yes. So this one for this neural compositional module, yeah, that takes as input basically the positive
the gear.
Yeah, exactly. The gear is the scheduling variable, and is then processing the positive values of the pedal, so the traction part of the pedal. And yes, and here we use the term fuzzify to create the activation functions. Yeah, right.
That takes the last gears.
Yeah, so it takes gear.last, so the last element, the current value of the gear,
and then we build the local model that is the compositional function.
So in this case, the gears range from 2 to 7, so we have 7 gears probably in our car.
Yeah.
With the 6 values. So, and then yes, this defines only the activation functions, and then we reuse them to define the local model, which would be what we call here compositional neural model. Exactly. Takes as input an FIR layer, because you see it from here. Yeah. So here you see the input is so we can have for each neural compositional model, as we've said, we can have an input function and an output function and an activation function and a number of channels. But okay, the input function in this case is a fully connected layer, right? Which we call FIR. So finite impulse response, because it compresses the time dimension in this case. And so, yes, the input function is simply an FIR layer. Again, we can have some intuition on the trained weights. Even in this case, we're expecting some exponential law or some exponential trend, if you want. So we can give it as an information. So please start with a guess that looks like an exponential. And then, yes, this is the definition of the. Okay, in this case, we have only an input function.
Yes. Yeah, in the other case,
we don't have. Yes, if we had also a function here, we could write it as output function equals something else. Yeah. And then we just say, okay, the local model, please take as input a past time window for the torque. So for the positive part of the pedal, a sample window with n samples there. and use as activation functions the ones that we defined, yeah?
The number of local models are the number of the activation function. So depending on how many activation function you define, you obtain a list of finite impulse response in this case.
So here we have 6 parallel models because we have 6 gears, and so 6 activation functions, 1 for each gear. Yes. And this is actually everything. Yeah, then we simply say that the output is the acceleration, and it's the sum of all the branches that we defined before. So sum of the aerodrag, braking force, gravity force, engine force. Simply taking a sum, yeah, simple as that, with a plus. You take the sum of everything, of all the layers, and that's it, yeah, basically. And then we simply say, okay, please add this model, right?
We create this object to compose. If you have, in this case, we have only one single estimator or model, and so we add just this single output. If you have multiple output, you can add the multiple output there, or you can create different models if you have an additional model.
So in principle, we can copy this line, add other models that maybe are then connected together in some way. Maybe one model estimates one part, one model estimates another part, and we can train them maybe all together at the end, or train only one module. So it's also powerful in this sense. And then we need to say, okay, what is our loss function? So an add minimize in this case, so a loss function, which is the acceleration error. This is a name that we can give. And the loss function is between the
acceleration
in the data set,
get from the data set, and the output of your network.
And the output of our model, So these are the 2 variables that we want ideally to be the same, the measured and the predicted acceleration. And the loss function is the root mean square error, And finally, we neuralize the model, and this number here corresponds to the time step that you have in your discretized time windows. So in this case, we're telling the model, please neuralize it, because here we said before we can take the input windows, for example, break dot sample window with a certain number of samples, but we didn't say what is the discretization. So here we said, please take 20 samples of the braking pedal. But what is the discretization? Discretization, you say it at the end, because it's a common property for all the model, right? So it's a discrete time model. Discretization time step is always 0.05 seconds in this case.
The idea is that you can discretize if you have a different data set, discretize it with a different time sample. You don't need to rewrite anything. You can just recreate the model.
Indeed, So in the data set, you can have a different discretization. That's fine. If you have a different discretization, probably the code interpolates automatically, right?
No, not yet, but
that was the idea. Yes, that's feasible. Okay, and then we simply say, okay, this is our data set. We simply load the data set, some filtering if we need, and then we train. Okay, training parameters, number of epochs, batch size, weight decay, whatever.
What I want to say, if you go up to the data set, what is interesting here is the how you load the data set, because also the data set, you just need to say what is the order of the column of your CSV, and the loading function will create a split, creating all the time window that you need. So you don't need to create and break your data set, creating all the specific window. Automatically, just giving the order of the column, you get all the data you need that fit your network. If you change the structure of the network, when you load the dataset, of course, automatically the dataset will shape compliant with the input.
So basically here in the dataset, we have some columns. You see the first row in the dataset is the headers. So the first column represents the velocity, and so on.
The torque, and this is the altitude, because we have the
altitude
in the space, because you have a vector that is representing the the altitude around the vehicle in that specific moment.
And here we just say we need the velocity column, the torque column, the braking column, gear column, etc. Yeah, very simple. And we just use them. Yes. And at the end, yeah, we just train the model with some commands, and that's all. We can also at the end export, yeah, very simply to PyTorch, in this case to ONNX, which is useful then to run the model in C++, right? So it's also powerful. With one command, you can export to basically ONNX and then load the model to C++, which is faster for inference, of course. So yeah, that's basically it.
This was
yeah. Do you have questions? Yeah, on the code? Yes.
Yeah.
Yes, in this case, the dataset was probably already discretized at 20 hertz.
Yes.
Yes, so it's probably important in the current version that the timestamp you put here is the same.
It's compliant.
It's compliant. Okay.
There is a feature that was implemented in one of the last version to auto-resampling the dataset in your specific. So if you, for some reason, you design, we have a dataset different, you can resampling when you load the data.
Yes. Okay. Other questions? Otherwise, I think, yeah, we can take a break, yeah, and then we see one or two other examples. Really, the first application, yeah, we've seen also the code with NNODELY, and okay, what about? So this was an application in the field of learning the longitudinal vehicle dynamics. We can see another application that is still in the field of vehicle dynamics, but it's a bit more challenging because here we want to learn the coupled longitudinal lateral dynamics from limited data, again, limited real-world data. And so here, okay, this is a work we did recently with a couple of visiting researchers at TUM and also in collaboration with Gastone. So basically here we were driving close to the limits our RoboRacer vehicle in our indoor test track, and basically collecting data to later train our models or deploying our trained models and trained controllers, in this case, to drive the car as fast as possible. So this is a work we did with Aniello Mongello from Napoli and Patrick Zambiasi from Politecnico di Torino. And yeah, we can, I mean, the overview of the system here is, again, dynamics learning for vehicles. But in this case, we don't have only one model for the longitudinal dynamics. We have also a model for the lateral dynamics. And the nice thing here is that we can take the output of the lateral model and feed it back to the longitudinal model, and also vice versa. We take the output of the longitudinal model, we feed it back to the lateral model. So in this way, we're really learning the coupled longitudinal lateral dynamics, which is important when we want to drive really fast, close to the limits. And each model is a model structured model or structured neural network. The inputs, the global inputs overall are the velocity, again, a pastime window for the velocity, pastime window for the steering angle, delta, and also the lateral model receives a pastime input for the acceleration, longitudinal accelerations. Note that this one remains inside the model, so we don't need it as a measured quantity if you want. So this is something that remains inside the model, and also this one, which would be the yaw rate, the estimated rate at which the vehicle turns. These two quantities in gray, they remain inside, so we don't need to have them as training signals in our dataset. Then we also want to have the motor current here, I, because the vehicle has one electric motor, which you control with some current. So you want to have the current as an input. Again, the velocity, the steering angle also for the longitudinal model, and this is the road slope if you have it, as before, like in the case of the altitude. And let's look at only one part. Let's look at the lateral model here. So here the idea is, again, let's use neural compositional models. In this case, we have a little less insights. I mean, we don't start from Newton equations in this case. We could even start from Newton equations, but we made a choice. Let's be a bit more, I don't want to say data-driven, but let's try not to start from Newton in this case. Let's try to start from the power of neural compositional models themselves. So in this case, we said, okay, let's try to model two things separately, to learn first the steady state behavior of the system, and then the transient behavior of the system. And so we have basically two neural compositional modules in this case, yeah, exactly, in a cascade connection. So the first one is learning the quasi-steady state, the second one, the transient. And the idea here is that, okay, we don't know so much for the lateral dynamics, at least for the to model the lateral dynamics, we don't know so much. We know something from experimental data. We know that if you plot the curvature that the vehicle executes, so the inverse of the radius, if you want, of the cornering radius, if you plot it against the steering angle, you obtain almost a line. If you fit it, you obtain almost a line, but the shape of the line depends on the speed. So again, here the model is locally linear if you want, and not only on the speed, it actually depends on the acceleration as well, on the longitudinal acceleration. This is something you would see it in 3D.
Yeah. For this reason, the local model here have three inputs. So
exactly, yes. So here we have basically the inputs, which are the velocity, steering angle, and the acceleration. And these are the ones that affect then the shape of this diagram. So we don't know much, but we know that this diagram has this shape. And we want to basically learn this diagram. So what we do, indeed, we use basically local linear models, because in this case, we know it's locally linear, to learn the shape of this diagram. Again, using activation functions, here we call them psi. They were called phi before, sorry for the confusion. But the activation functions, again, they are functions of steering angle, velocity, and AX.
So in this case are not anymore one dimension, not b-dimensional, but are three-dimensional. In
this case, they are three-dimensional, yes. So they are in 2D, they look like pyramids. In 3D, they will look like hyper-pyramid, yeah, if you want, because in this case, we're still using triangular activations. And so basically, we have hyperplanes, if you want, local hyperplanes that approximate or learn the shape of this diagram. And we're not telling much, actually, to the model. We're just telling it, please use hyperplanes, local hyperplanes. That you can see in the form of neural compositional modules. So here you see, this is our input function, again, for the neural compositional modules.
In this case, there is no any.
Yes, we don't have an output function here, because we want to learn a static relation. This is a static relation. So we don't want to have finite impulse response layers in the output, because we have no dynamics to learn here. It's just a static map, steady state map, that tells us what is the shape of this diagram, basically, intuitively. And then in the transient dynamics, yes, here we want to learn the dynamics. So here we will have fully connected FIR layers
As input.
As output, yeah, in the output functions. And here the intuition, so here the intuition was the shape of this diagram. Okay, so here we said we know from experience what is the shape of this diagram. We expect it, yeah. Here in the transient dynamics, there is not much we can expect, but we can still expect that when we steer with our car at low speed, we will get a very different behavior from high speed, yeah. So steering in a parking lot is very different from steering in a motorway. So we know the transient dynamics will depend on the speed. So for sure, we will need here to have activation functions that depend on the speed. So we will need to learn the dynamics in different ranges, in different regimes of speed. And same thing for the longitudinal acceleration, right? If you steer while accelerating, maybe you skid, right? Or maybe you lose the rear, or strange things can happen. And so you need to consider that, both the speed and acceleration. So this is the only physical insight we give in this case for the transient dynamics. So we have different local models, different branches to learn the transient dynamics in different ranges of speed and acceleration. And at the end, of course, we sum everything. And this is the shape of the activation function. So again, triangular activations. In this case, you don't see the full triangle because we have only two activations, because we have we choose to have only two. We actually made an analysis. These are hyperparameters, if you want, yeah. So we can then tune the hyperparameters of our network, become the number of local models, the number of the length of these input windows. This is another hyperparameter, but we don't have so many, so we can actually tune them quite easily with a grid search or something like that. Yeah, so in this case, we have a continuous activation function, so piecewise linear. Yes, this is the interesting thing. So can we then inspect, or can we then interpret the behavior of the trained weights? So in this case, we have, so this function is learning static things. This neural compositional module is not learning dynamics. This one is learning dynamics. And in particular, these layers are learning dynamics. Yeah, these fully connected are learning dynamics, because basically they need to combine the past history of these input windows. This module here still returns a vector. Okay, so if here we have q+1 values as input, here we will still have q+1 values. Okay, and the last one will be in the present, previous ones will be in the past. And then these layers will need to combine them. And if we look at the trained values for the weights, they
we have four layers, no, for finite inputs response, because we have 2 multiplied by 2 activation function in velocity and acceleration.
So these are the activations for the velocity. These are the activations for the acceleration. We have 2 and 2, so we have in total 4 local branches, 4 branches. And so we have 4 fully connected layers here to analyze. And if you see, almost all of them have this interesting trend, so which is very interesting to analyze, because indeed, if you move towards the present time step, okay, so so the weights that then multiply the values close to the present of velocity, steering, acceleration, the ones multiplying the present are higher, so they have higher values than the ones multiplying the past. So in this case, we can also see that our system is basically losing. I mean, the past is losing its importance when we go to the past. Yeah, of course. So when we go to the very first samples we feed as input, those samples have a very limited importance on the output. Yeah, this is what the graph is saying.
From here, you can see that there is no delays.
Yes,
The
exactly.
delays are not appear here. Otherwise, you have otherwise the peak of information will be shifted a little bit in the past. Okay, so because the most important weights are at the present, means that there is no a delay that is more than the sampling rate. More.
Yes.
Otherwise, you will have the second or the third or the fourth more high. Okay.
Yes, and indeed, this is a physical intuition. And this is why, actually, also in the previous example, we said we can tell the model, please do not start from random noise when learning, or from random values when learning these weights, but please start from a shape that resembles an exponential. Because here you see this shape is actually resembling an exponential somehow. And if you start from that shape, then the model is faster to converge. You have lower risk of finding bad local minima, non-physical local minima.
Yeah. Sometimes it happen if you, for example, if you just initialize with random weights, you can get a good fitting, but if you have a look on the weights here, maybe are completely noisy. So means that if you filter them, probably you get something close to this, okay? But you have included some high frequency information in your fitting. So a good way is to initialize to avoid this during the training. Yeah.
Yes, indeed. Yeah, and this helps. Then also gives you information. If you find that, so in this case, the pastime steps were really having not so much importance. So one can also say, okay, I will then run a second training in which I just exclude the samples that are lying so far away in the past, and I just shorten my input window to include only the most recent 10 values instead of 15, like in this, or 20, like in this case.
Yeah.
One can also do that, yeah, and then you get even more physical intuition.
I mean, for example, if you look to the red one, seems noisy, but is have some oscillation that probably is not completely noise. Okay, if you look at the red one, you see that it's going down, up and down here. So probably it's something that is plausible. No, it's not completely just random up and down. So you can perceive a shape also in the yellow one. So probably are not completely noise there. Yeah.
Yes, indeed. So this basically is a plot or a representation of your frequency response of your system, yeah, of your dynamic response of your system, of your impulse response, if you want to be more precise.
So if you are single pole, probably is something that is going to zero. But if you have a second order or multi-order, probably you have some oscillation. So yeah,
yes,
this is captured from to the network.
Indeed. And here we're comparing, okay, we're comparing the model, our model, the model structured one in green, against other versions, yeah, general purpose one. And you see, especially with a small, so here we had three types of data sets, yeah, a large one, medium one, and small one. With a small training data set, you see, we can then have still a validation set that is different, yeah, of course, from the training one. And especially with a small training data set, we can outperform significantly the general purpose one on the validation set, which is never seen. So you see, we basically improve by 50%, yeah, the performance in RMSE. The last one, the second indicator is the FVU, which tells us the fraction of variance unexplained. It's basically 1 minus the coefficient of correlation, the R squared, which you may know. But yeah, okay, so the take-home message is we can have a better generalization with smaller training data sets thanks to the physical intuitions that we can inject, which are not so many. Like in this case, we didn't really start from Newton equations, yeah? We just injected some physical intuition, but it worked out better than nothing, yeah, at the end. And here we also show that we can quickly adapt. So what happens if we change tires, yeah, in our RoboRacer, in our small-scale vehicle? We change the tires or we change the mass. We can also increase the mass by 10%. And basically, it turns out we can quickly adapt to new conditions. So we can still zero-shot generalize without fine-tuning. But if you want, you can also selectively fine-tuning your model. So with a general purpose network, you have no option to selectively fine-tune. You need to fine-tune all the model, basically. With this model, you can also say, no, I want to fine-tune only one part of the model. So basically, I know my tires will maybe change the transient dynamics. We expect the tires to be changing more the transient dynamics with respect to the steady state. And so we can selectively fine-tune only the transient neural compositional module. And it actually works, yeah. So we did like that. We fine-tuned only one part of the model with only 20 seconds of new data with the new tires. and change the mass also, plus 10% mass. And you see in all cases, we're basically outperforming, this is the lateral dynamics, this is the longitudinal, before and after fine-tuning, you see we're outperforming the baseline GNN, which is the general purpose model, in basically all cases, yeah. And this is advantages because we can quickly fine-tune. Actually, we fine-tune only for 50 or 60 epochs, I think.
Yeah.
So very quickly, you can also do it in principle online, and it can be effective, yeah, especially when your conditions change. Yeah.
And then you have the implementation. I don't know if you want, because we are, yeah.
Yes. If you want, I can quickly show you the code, yeah, in NNODELY. This is also, so yeah, the model actually looks simple, but there is a lot of local models here, a lot of connection stuff that changes. So
here also you are showing only the lateral
This is the lateral, yeah. Then we have also the longitudinal dynamics here. But here I didn't want to spend too much time, so we just looked at the lateral model. Just very quickly, yeah, I can show you the NNODELY code, and then we probably close. So once again, yeah, the idea is similar to before. The longitudinal, and then we have the lateral dynamics here. So here, okay, maybe the code is a bit longer, but we can optimize it and make it shorter. Actually, here we are defining again our inputs. So once again, yeah, the inputs for
maybe just the lateral model.
Yes, yeah, we can maybe keep here. So the inputs are again the velocity, steering angle, and acceleration for our model. So yes, we report them here: velocity, steering angle, acceleration. And we want the output to be the yaw rate, yeah. So the rate at which our car is yawing, yeah, is turning. And okay, then we have simply some normalization quantities. Yeah, we want to maybe normalize our inputs. We want to have 20 time steps in our past windows, yeah. So these past windows have 20 time steps. Again, this is related to physical intuition, as we said before. Yeah, we can have our number of local models here of parallel channels. We also call them channels sometimes. And it's 2 channels for the velocity, 5 channels for the steering angle, 2 channels for the longitudinal acceleration. These are design choices. Yeah, these are hyperparameters. We tune them in such a way to be to balance the trade-off between complexity and accuracy on the test dataset. And then these are the centers. Okay, we want to maybe have an equal distribution of the models of the centers on our domain. And yeah, okay, and then basically here we're defining what is the shape of our local model. So what is the shape we want to have in this part here? These models, we said we want to have local hyperplanes, so linear models, but each model needs to have different trainable coefficients, different trainable parameters. And so we're doing that here. We're saying, please, each model needs to have their own parameters, yeah? So every time we call parameter means
create a parameter.
We just create a new learnable parameter, yeah? This will be its name, and we can have some initial values for that. In this case, we don't have a lot of information. Yeah, we just say, please use 1 to the minus 5.
A small, very small.
So a small value. We don't have physical intuition in this case for the weights of these hyperplanes, for the parameters of the hyperplanes. But maybe we have a physical intuition for the fully connected. Yeah, once again, they need to look like exponentials. And so, yeah, we just use Fuzzify then to create our activation functions for the velocity, for AX. This is for the transient dynamics, yeah. So these parts here, and same thing, yeah, exactly. Same thing for the steady state, yeah, which will be here.
And what you can show maybe when you combine the fuzzification function there.
Yes.
You know, if you go on the other circles here, yeah, you can see if you want to create a multi-dimensional fuzzification function, it just needs to list the activation function here, 1, 2, and 3, and the framework will take care about to creating a multi-dimensional activation space.
Yes. So this would be this local model here, this neural compositional model here. You see we have 3-dimensional activation functions. So we can basically pass to the local model function all the 3 activation functions, and it does it automatically.
Yeah.
And our inputs are again a sample window, SW of steering angles, velocity, acceleration. Yes, with their number of past samples. Yeah. So
and
yes,
we have the understeering function that is a nonlinear function that is defined in the
yes, this is the input function. Yeah, so it's the one we find here. We have no output function in this case, so no worries. Instead, for the transient dynamics, yes, we have the output function. We don't have the input function. So the output function will be an FIR, yeah, finite impulse response layer. Again, we want the weights to be initialized with an exponential because of the physical intuition behind it. And we want the transient dynamics to take as input
the output
of the quasi-steady state, yeah, and to use these activation functions, yeah. Yes, exactly. So that's it. Yeah, basically this is the model. The output will be the overall output is the output of the transient dynamics, yeah, part. And that's it. Yeah, then we just need to initialize our model, add the model.
Here you can see that you are creating this composition to this simple architecture, and then you combine, because here is creating the model for the estimating the yaw rate. Then in the next part of the code you have to create the local model to design the longitudinal dynamics, and then you can combine. Maybe you can spend 2 words about the connection.
Yes,
just
it's not so clear where we did
you
that
combine,
actually.
okay.
Yeah, we did that here somehow in the closed loop. So basically here we have
because this is something that is not easy maybe
indeed. Yeah, we can maybe show that. But I need to find the part in which to do. Maybe tomorrow I will show you. Yes, now I'm not super sure where.
There is a simple way to combine and connect different models that are working together, because also here there is important to say that here you need to remember a past window in time, and so the framework will help also to take into account this past window when you connect two different models together. So
yes. So maybe tomorrow we also show you how we do it in NNODELY, how we combine 2 models together and we can then train them together.
And this double chain of connection. This is what I want to mention. Yeah, doing this architecture using standard framework, you need to do with care. Here it's more straightforward because you are sure that some specific needs are preserved, and you are doing the right stuff during the training.
Yes. Indeed, yeah. So questions here on the code or on the application somehow?
What is this? There's the part of control.
Is there a way in general
Yes.
So you said that you changed the tires and you optimize only that thing, but actually maybe between 2 tests, other things could have changed them. So you're actually locking everything except the tires, and so every type of change will be affecting only the tires. Is there a way to maybe train all of the model, but mainly the tires? And
yeah, you can during the training. You can identify different loss gain to different part of your weights. Okay, so you can say, okay, this part of the model get a specific loss function, and you are minimizing with a different for parameter. Cioè each parameter can have a different learning rate, and so you can use, or if you have different loss, you can adjust with different loss with a different gain, or on the specific learning parameter. Yeah.
Indeed, yeah. So in the loss function, we can have different terms. In this case, we only had one, but in principle, we can have more than one. And then when fine-tuning, we can also selectively fine-tune one model or the other, or one part of the dynamics or the other, yeah. For example, by acting on the loss function, or by indeed unlocking or freezing parameters. Yeah, exactly, yes. So we can say for each parameter if it's trainable or not very easily.
Or also choose exactly the learning gain on the specific parameter.
Yes, exactly. Yeah, we can also adjust selectively the learning rate for individual parameters. Yeah.
But if I want all the parameters of a single layer to be changed to a specific rate, is there a way to do it?
Yeah, commonly the parameter in the code was mentioned. Parameter have a name, no, and you can just selectively say this parameter with this name have a specific learning gain, and you adjust.
So here in the definition of the parameters.
Yeah, for all the parameters of FER. Yeah. In this case, we not give a name of FER, but you can in principle give a name and recall this name in the training to adjust the learning rate. Yeah.
Or you have a lot of parameters that you want to selectively change over train. Once I did it in this way, so I added that one to another model. So when you do add model, you can, for example, generate time model, and you have part of the network that is under that model. And then you can also select only the model that you want to train.
Okay, yeah, maybe we can repeat it for the ones online. Yeah, so you can actually selectively probably freeze or unlock.
No, what he said even that you can decompose your model in more multiple model, and then decide that the specific model have a specific learning rate.
Okay, yeah. If you have different models, so added like this, so you have one add model, but you can have also other add models.
Your model in additional block in multi blocks, and then you can select leave or train or decide the learning rate.
Yes.
Or the other possibility is give a name of the parameter and then choose the
Okay, yes. Other questions on the application or the code? So otherwise, I would say we can maybe close for today, and tomorrow we see the last applications. We have one other application. So these models are learning the dynamics. We have another application in which we learn a controller, actually.
I think it's not better to do today.
Yeah, but maybe it also takes some time. So I would say we can maybe do it tomorrow, but quickly. We won't spend too much time on that. Then we will see an example in which we can train a controller through a pre-trained dynamic model. This is also interesting. So you can train the controller basically with unsupervised training. So without collecting new data, you just train the controller to operate very well with a pre-trained simulation model or pre-trained dynamic model. And then we show another couple of examples. So with NNODELY, you can also implement physics-informed neural networks, so acting on the loss function. Then I will probably show you a couple of examples with foundation models. So foundation models that inject somehow physics priors inside their operation. And finally, we can close with maybe some of you that if you have some ideas on how to embed these ideas or create new ones for your own research, we're also happy to discuss.
Yeah.
Both the ones in
particular,
presence and online.
The one want to make to get the credits. If you want to already start to think about what can be the application of not only our technique, but in general the technique we saw. If you are interested to maybe open a discussion of your topic, we are open to it.
Yes, indeed. Yeah, we will also have some time tomorrow. So officially tomorrow would be until 11, from 9 to 11. But we can take an extra half an hour and discuss some ideas you may have, the ones in person, but also online. So yes, we're very open to do that, and yeah, looking forward to that.
So online, I don't know if probably online they don't need the credits, but
No, some people online, I know they also need
okay.
the credits. So, but in any case, apart from the credits, if you want to apply these ideas to your own research, we're also happy to help you and discuss which possibilities there are. So, yeah. Also, yeah.
What I would say that also I have in my group of research there is other PhD that can help that can support you to try to in particular to use our software or in general our techniques. So if you are interested to use please let us know.
Yes, indeed, yes. So yes, we can also support with the framework and everything, of course. Yeah. Okay, good.
Okay.
Yeah, I think we can, if there are no questions, we can close for today.